So the chapter we are going to start today is acid-base chemistry. Acid-base chemistry is a fundamental aspect of chemical science. It describes the concept of acids and bases as well as their interactions in aqueous solutions. Acid-base reactions are essential in various chemical processes from biological system to industrial applications and are often visualized through pH of solutions. The pH. The pH scale was originally introduced by the Danish biochemist SPL Sorensen in 1909 and used the symbol pH. So basically he was the Danish biochemist. Okay, he was a Danish biochemist and his name was SPL Sorensen, and in 1909 he used the symbol of pH. The letter P is derived from the German word potens, and which means power or exponent in this case. In 1909, SPL Sorensen published a paper in Biochem Z in which he discussed the effect of H-positive ions on the activity of enzymes. In this paper, he invented the term pH. So, it's basically hydrogen 2 in Latin to describe the effect and defined it as a negative log of concentration of H. In 1924, Sorensen realized that pH of a solution is a function of the activity of the H positive ion, not the concentration. Then he published a second paper on the subject. A better definition he proposed was pH is equal to minus log concentration of H positive. Okay, now we are going to discuss where H positive denotes the activity of the H positive ion. The activity of an ion is a function of many variables of which concentration is given. Okay, concentration is abbreviated by the square brackets. As we all know that we use the concentration term, write the concentration terms in the square brackets. For example, for the hydronium, we use it in the square brackets, and activity is abbreviated by using a with curly brackets. The concentration of hydrogen ion in aqueous solution can be expressed in terms of pH scale. The pH of the solution is the logarithm to base 10 of the reciprocals of the numerical value of the hydrogen ion concentration. pH values of the bases is basically for the negative log of hydroxyl ion concentration, and if we have to relate the pH and pOH, we use the term pKw, which is equal to pH plus pOH. At 25 degrees C, the pH plus pOH is equal to 14. Okay, now we have the pH scale. pH scale is a numerical scale that shows acidic or alkaline strength of the solution. So what it shows the acidic or alkaline strength of the solution. The value on the pH scale goes from 0 to 14. Extremely acidic substances have a value below 1, and all acids have pH values less than 7. So the lower the pH, the more acidic the solution is. The higher the pH, the more alkaline the solution is. So here we can see in this chart that when we have the values that are from 0 to 6, then we have the increasing acidic strength order, and when the values are from 8 to 14, we have increasing basic strength order, and for the 7 we have the neutral value. For example, when we have the water, so its pH is 7, so the water is basically the neutral solution, and if the solution has pH 3, then it means that the solution is acidic, and if it's has the pH above 7 like 8, 9, 10, so it has the basic nature, like we have the sodium hydroxide, potassium hydroxides. So these are the bases. Okay, now Now we will see that pH is indication of concentration of H positive ions. So it is basically the definition of pH. For example, at pH of the 0 the hydrogen concentration is 1 molar, while at pH 14 the hydroxide concentration is 1 molar. Typically the concentration of H positive water is most solution fall between a range of 1 molar and 10 to the power minus 14 molar. So here we have the scale in which the pH of different solution is given. For example, for the battery acid, for the lemon juice, for the pure rain, freshly distilled water, sea water, and for the gastric fluids, so for the milk of magnesia. So different solutions have the different pH values. Okay, now we have the example 4.1. so we will look at this example. Now in this example we have to calculate the pH of a solution 0.002 molar. So we just simply put the value in the H positive. This is H positive ion concentration because HCl is an acid. So we will find the pH value. Negative log 2.0 into 10 to the power minus 3, we got the pH 2.70. Similarly we can find, if the pH is given, we can find the hydrogen ion concentration in the second example. Now we have another important topic, that is ionic product of water and calculation of pH and pOH. Recall that the product of concentration of H positive and OH negative ions in pure water at room temperature is 298 Kelvin. Kw is equal to H3O positive and OH negative, where Kw is the ionic product or dissociation constant of water. Unit of Kw is mole square decimeter per decimeter minus 6. In pure water, the concentration of H positive OH negative ions are equal, that is 1 into 10 to the power minus 7. So the value of K water at room temperature is 1 into 10 to the power minus 14. pKw will become minus log of K water. So ionic product of water is related to a dissociation constant pKa and pKb of an acid. So pKa plus pKb is equal to pKw is equal to 14 at 298, and pH plus pOH is equal to pKw. So if the pK value of acid is known, the pKb value of its conjugate base can be found by using this formula. Okay, now we have another example, that is example 4.3. If the concentration of NaOH in solution is 2.5 into 10 to the power minus 4, what is the concentration of H3O positive ions? OH negative ions concentration is 2.5 into 10 to the power minus 4. And now we have to put these values in the equation, and we got the final answer, that is 4.0 into 10 to the power minus 11 molar. Okay, now we have example 4.4. this is also the same, which we just have to put the values of OH negative ion concentration and Kw value. So just dividing with each other, we got 1.0 into 10 to the power minus 11 mole per decimeter cube. Now for calculation of pH, we will put this value in this equation, and we got the final answer, that is 11. Okay, now we have another example 4.5, in which the value of OH negative is given, and we have to calculate the pOH. So first of all we will calculate the pOH, that comes 4.30, and after that we will calculate the pH by substituting this value in that, and got the final pOH value, that is 9.70. Alright, okay, Now we have the next topic, that is pH titration curves. pH titration curves, what are they? In order to determine the concentration of the unknown solution, the technique of titration is used in neutralization reactions between acids and alkalis. It involves adding a titrant of known concentration from a burette into a conical flask containing the analyte of the unknown concentration. An indicator is added which will change the color at the end point of the titration. The end point is the point at which equal number of moles of titrant and analyte reacts with each other. The equivalence point is halfway the vertical region of the curve. So equivalence point is gives us the moles of the alkali, which is equal to moles of the acid. So while doing the titration titrations in chemistry, we just use the neutralization reactions. We perform neutralization reaction adding a titrant into the burette and analyte into the flask. So when equivalence point is achieved, so equivalence point is the point at which neutralization takes place. So equivalence point is the point at which the neutralization takes place. There are different types of titration curves depending on the strength of acid or alkalis used. Strong acid and strong alkali pH titration curve. So in this case, hydrochloric acid is taken in the conical flask. Initially there are only H positive ions present in the conical flask. As the volume of strong alkali added from the burette increases, the pH of the HCl solution slightly increases too, as more and more H positive ions react with the hydroxyl ions to form the NaOH. So initially the pH is low, but when adding the NaOH, the pH gets high. The change in pH is not as much until the volume added gets close to the equivalence point. The pH surges upwards very steeply. The equivalence point is the point at which all the H positive have been neutralized. Adding more NaOH will increase the pH as there is an excess in the hydroxide ions. So this is the curve that shows the titration of HCl with NaOH. So at the initial the pH is low, but when the alkali is adding up, so there is the final pH that is about 13.5, and this is basically the equivalence point. So at this point the acid and base neutralizes each other. The pH titration curve for HCl added to NaOH has a same shape. The initial pH and final pH are the other way around. The equivalence point is still 7. Following figure represents the pH of the titration curves. Okay, the diagram shows a pH titration curve of 1.0 mole per decimeter cube NaOH with HCl. So when HCl is added, so equivalence point will remain same, but the curve will become basically initially pH was high, but at the final it will become the lower one. So this is the difference between the titration of HCl with NaOH and titration of NaOH with HCl. Okay, now we have another topic, that is strong acid and weak alkali pH titration curve. Initially there are only H positive ions present in the conical flask. As the volume of the weak alkali added from the burette increases, the pH of the analyte solution slightly increases too, as more and more H positive ions react with NH3. The change in pH is not that much until the volume added gets close to the equivalent point. So it is basically the titration of NH3 with the H positive ions. The equivalence point is not neutral, but the solution is still acidic. This is because all H positive have reacted with NH3 to form NH4 positive, which is relatively strong acid, causing the solution to be acidic. As more of the NH3 acid, the pH increases to above 7, but below of the strong alkali, as NH3 is a weak alkali. Following curve represents the reaction. So this diagram shows the reaction between HCl and NH3. So in the initial pH was about 1, and equivalence point is achieved at the pH 7, and after that we got the pH of 11 as the final pH. So pH increases, but it will not increase as much because the NH3 is a weak alkali. So it's basically a titration of strong acid with weak alkali. Okay, the equivalence point here is still about 5.5. Now we have the reaction between weak acid and strong alkali. Weak acid and strong alkali. So initially ethanoic acid, which is a weak acid having initial pH of about 2 to 3, is taken in the conical flask. As the volume of the strong alkali added, the pH of ethanoic acid solution slightly increases too, as more and more H positive ion react with hydroxyl. The change in the pH is not that much until the volume added gets close to the equivalence point. The pH surges upwards very steeply. The equivalence point is not neutral, but the solution is slightly basic. This is because all the H positive in acetic acid have reacted with hydroxyl ions. However, CH3CO negative is a relatively strong base, causing the solution to be basic. As more of the NaOH is added, the pH increases to about 13 to 14. So this is the curve. Initially the pH is in the acidic region, but the equivalence point is achieved at about pH 9. Okay, in this you can see here that this is the equivalence point. It is about at pH 9, and here we can see that there is a slight increase in the pH, and the pH surges very steeply upwards. So here the hydroxyl ions have reacted with H positive, but when we got the conjugate base, we know that the conjugate base of a weak acid is always a strong base. So we have the strong base here, which is a conjugate base. CH3CO negative is a conjugate base of acetic acid. So this causes the solution to be basic, and the pH increases to 13 to 14. Now we have the weak acid and weak alkali pH titration curves. Weak acid and weak alkali pH titration curves. Initially there are only H positive ions present in the solution from the dissociation of weak acid and weak base. So first of all, the pH is about 2 to 3. In this pH titration curve there is no vertical region. There is a point of inflection at the equivalence point. This curve does not provide much information. So here we have the equivalence point at about pH 5 or no, not 5, it's about 7. So at the equivalence point is about pH 7, and there is not a very large change in the pH, and the alkaline region is existing at about pH 9. So okay, so this is basically the reaction, the titration of the weak acid with the weak alkali. So I hope that you got this lesson. Thanks for listening. See you later.